Okay, folks, I think we're ready to resume. So, first of all, this is now the start of the hands-on part. You will be guided through this by the talking head in front here, showing you what to do. There are also workbooks being distributed in paper form to the tables. Furthermore, we created a little website, which is the homepage on the Black Dell notebooks that you're going to be using. This is also available on the internet, at least it should be, P4CDevCon.netronome.com. And you can go to that site. It's only available today, special for today only. And you can click on Workbook Lab 1 to get the same content as you would have on the paper.
Can we download this for later, or is there, so we can review, or should we just archive it?
I think it's probably okay to download, but let's distribute it to you in PDF format. That's going to be more convenient. We made it HTML for easy cut and pasting into the development environment. But if you want to kind of archive it, we'll give it to you as a PDF for later. Okay, and we also have biological assistance here today. So I don't know if you remember the old school Windows wizards that actually walk you through something step by step. So we have today here the P4CDevCon wizards. They respond to audio commands, so they're similar to Siri and Cortana, etc. But you can drag them around, but don't drop them. Don't click on them. Don't double click on them. But so I'll try out the first audio command and say we're going to introduce them now. David George over there. And then we have Mary, Nick, and Chris, Awanish, Simon, Rando, Edwin, and Bidat. Okay, so if you get stuck at any point, use your voice command function, say wizard, and then they'll activate and come and help you. Okay, so the paper workbooks will guide you through this, but I'll also try and do it from the front here. So we have a few slides on each to just explain what we're trying to achieve, and then we'll be diving into the actual code. So the goal of the first lab is to implement a wire connecting the network and the host back to the network. So such a wire is called a NIC. And that may seem like a small step for mankind, but it's really the first step you need to do, because after you've done that, you've now got this processor able to run P4 and C in the middle. And now it's just a simple matter of writing code on to make it more intelligent. So this is going to be the basis of the following labs as well. To do this, we're going to look at the integrated development environment. There are some elements in there like projects and files we need to understand, and some workflows to take us through the whole software development process. As far as P4 constructs, the P4 language is, in my opinion, not that great for very simple things, because it forces you to declare a match table. Even if you want to always do a hard-coded action, it forces you to put an entry in that table. It's being discussed now, we heard about it yesterday, to make the default declarable in the language and so on. But we still on the old language, so we'll be showing you how to do parsing, matching, and actions just to do a wire. Anyway, This is now hands-on, so please type on those Dell laptops, cut and paste from the HTML-based version to save you time. See it run, debug. You know, this is your chance to play with it. And please also ask questions. So the workflow we're going to follow in the IDE is we're first going to create a project and then add files to it. So the files in a typical project include P4 files, C files for the sandbox. There's rule files that have this initial table data that we just talked about. There's editors for all these. For P4 and C, it's just text with syntax highlighting. For rules, there's actually more like a dedicated GUI editor to create the rows in the table. Building the project is needed at certain strategic steps. We'll cover that. For running and debugging, you'll use those standard NICs we have in the servers to inject packets with TCP replay, to look at them with TCP dump, and that's kind of the workflow. In short order, you should be able to have your NIC product ready to ship. Just add hardware. So the elements here, a bit more detail about how the programs work. Your P4 parser is going to decode and extract the packet headers and keep them in local memory in the actual register file of the NIC processor. This is very fast memory. You can access it in one cycle. So after the packet headers are sucked in there, the matching operates on them, effectively an algorithmic TCAM. We can talk a bit more about the algorithms and things over a beer later. The actions are going to modify the extracted headers in the same local memory. So it's also very fast to modify them there. And then they get flushed out to the actual packet. The packets are, in this case, also kept in on-chip memory. It's a bit slower than the single cycle one, but the packet data can also remain on chip. And P4 forces us to declare the overall control flow as well. And you'll see that in the P4 code. So the expected behavior of this is that we want to achieve a wire, but to make it easier, we say put even a smaller step in front, drop all the packets. And then we're going to change the table entries to actually make the wire work. So the ports on the NIC are called P0 for the physical. V0.0 will be our port going to our first SRIOV virtual function, also being the first NetDev. And that's why the wire needs to do the incoming and the outgoing direction. Okay, so without further ado, if you can fire up your Programmer Studios if they aren't running yet. And now we're going to go and create a new project. Important, make a new project, not just a new file. So it's a difference between file new and file new project. So you can follow along. I'm calling this the P4 Lab project. There's a large number of chip families and variants there. We are going to pick the 4XXX B0 because that's a generic name for the chip on these NICs. And now very important, remember there's the two perspectives. There's your perspective where everything is automatically placed, and you just write your P4 code to do parse match action, and you have to click this checkbox to activate that mode. if you don't do that, you're going to get into a mode where you have to do everything yourself, which we'll do in the later labs, but for now, click P4 there. Okay, now we have a project. You can see on the file view on your right, the files in the project. There aren't any project files yet. So now we want to make a file with our P4 code. And we want to select, so it's file new or control N. We're going to select P4 source file and click OK. And now we actually have an editor with P4 syntax highlighting capability. So now for the people that can type quickly, you can now type however you want the P4 code. But for the lazy ones among us, I'll just go and cut and paste this here. Okay, so let's have a look a bit at the code. What does this code do? We are declaring an Ethernet header because, as we discussed yesterday in the conference, people are not interested in replacing Ethernet yet. That's burnt into the max. Your frame check is kind of in hardware and so on. So everything we do will still be based on Ethernet. So we declare an Ethernet header. First declare the type, and then declare an instance of the type. And now we declare a parser. The parser always starts at the start node. So that's where we're saying, when you start, parse Ethernet. The Ethernet just extracts the Ethernet headers, putting them in the local memory like we discussed, and then returns ingress. So ingress will jump to the control flow here, which applies the in table. And that starts your matching process. The in table doesn't match anything. It just says drop. But you still need to declare drop as a kind of an action subroutine, as an action function. So this is all very complicated way of saying drop all the packets. But in any case, we've got that now in the editor. So I'm going to save it and give it a name, P4 lab, for example. And now we have created our first P4 program. But we still need to add it to the project. So we are going to go now to the build settings dialog and insert the file into the project using that insert button there, and click on open in the file viewer to insert it. So now the file is part of the project, but it's not yet the root file because the system starts to compile from the root file. So we have to choose the P4 file from the drop-down and make it the root file. Click on OK when done. Remember the voice-activated wizards if you ever get stuck with this. Are people managing to follow along? It's pretty simple, right? Okay, so now we are basically already at step 8 in the workbook. We, by default, to the earlier question, we do support simulation. In fact, it's even the default in the system. But in this case, we want to activate hardware debug because we will be using real NIC hardware here. So debug menu, activate hardware. And now we can go and build the project. From the build menu, we can choose build, or you can just press F7. Okay. So we can now see the build output here. Assembling and compiling and linking and whatever the system does. If we had a mistake in our speed typing, it would have given a message, and if you click on the message, it takes you to the line. That's the problematic line. While we're waiting for the build to complete, you can also look at view IR graphs. And these IR graphs are generated from that intermediate representation. Remember the diagram where P4 gets compiled to the intermediate representation and from then compiled to the firmware. So you can actually go and click on these graphs to jump around in the code. And this visualizes for us the pass graph and the ingress graph. Okay, so we are done with building. Now we need to go and add our rules. P4 language doesn't allow us to put it in the P4 program, so we have to add it as a separate step. So we go File New again, choose P4 Rules File, and we see the rule editor. Now we need to select a table because we're adding the rule to a specific table. There can be many tables listed here, so you have to select which one you want to work on and then click Add. Now we have a space for an unnamed rule. So we're going to just call this default and select it has to be the default rule and choose the drop action. And now we are basically done with saying by default drop. So we're going to go ahead and save that by saying Control S. And again, call it, for example, P4 Lab. So, congratulations. You are now an SDN controller. You are able to create a match table entry. And, okay, I don't think you're going to put Open Daylight and OpenStack out of business, because you don't want to do this for every single flow entry they make. But maybe worth thinking about whether you want to go into that business. So similar to before, we need to add the rule file to our project. So we're going to insert the P4 rules file using the dialog on build settings. Going to open it and make it the root file, the main rules file. Exactly what we did before with the P4 code, we now did with the P4 rules. And we can hit OK. So at this point, we're ready to rumble here. We want to go and execute this and see what it does. So first of all, we do need to type in our hardware debug options. So this is the hardware menu options, and say we want to connect via Ethernet to our debug server. So the way this works is you have your Windows system running your GUI, your debug session, but the actual NIC is plugged into a Linux system. So we have to now say what is the host name or IP address of the Linux system. So we've made it easy for you and pre-configured it that you just have to type my-NFP there. So normally that would be an IP address, but we made it a bit easier. Okay. Yes. Yeah. It is a server address, yes. So we kind of cheated a little bit. Yours is called my-NFP, mine is called my-NFP, so there's many my-NFPs here. So they're actually different servers, okay? So we're not going to conflict with each other. So each laptop is configured to have my-NFP, the correct IP for that laptop. Okay, so we ready to do hardware debugging. We specified our hardware debug options. And we can now click this bug icon or use the menu or hit F12 to start hardware debugging. And it wants us to rebuild How are we doing so far? Are we able to? Are we able to debug it? Sorry? Okay. I'll pause a little bit for people to catch up here. So to just explain what happened now, it created a firmware file, which is an ELF file. It's the normal files that Linux also creates, but it's with the code for our processor, our special RISC networking processor. And the front end here actually sends that firmware file to your Linux host, and it will go and get loaded into the chip. Normally, when the NIC boots up, these files are just put in /lib/firmware. So they normally just loaded from there. You can also go and burn these firmware files into flash if you prefer. And then it'll be up and running even before the server is ready. So if you want to do something like Pixie boot, etc., then it's advisable to have a bit more pre-configured in the flash. But in any case, we Okay, I think it's time to move on. So the debugger starts up with a picture of the entire chip here. So as Gavin explained, there are many islands, there are many cores called micro engines, and we've configured these systems that to make it simpler, that we know traffic is going to go to micro engine on island 32 when we send in the first packet. It is predictable, and we do know that that will happen. So we want to go and open micro engine I32:0 and double click on thread 0. So this opens up the debugger and the source file that's loaded on that. But we now want to go and, using this drop down, select the P4 file, because we want to debug at the P4 level, not at any other intermediate code level. So we double-clicked thread 0, we chose the P4 file there. And now we're going to go and right-click in the margin and say display instruction addresses. The reason for doing this is it just makes it easier to see where we can put things like breakpoints. So I'm just going to go and sprinkle breakpoints through this. To add a breakpoint, one can go and press the F9 key. Or use the menu. Okay, how are people doing? Are you able to open the debugger, set breakpoints, etc.? What I discovered here is that it's not such a good idea to move your toolbar off screen so you don't see it. So. But this toolbar can be dragged off screen, but it's not such a good idea because it's hard to click off screen. So we're going to go ahead and using the toolbar, set a few breakpoints. There is a button to remove all breakpoints. Are you maybe already running? Yeah, then you need to press the traffic light to stop running. And then you can remove the breakpoints. So, okay. So now we're going to, just a bit of theory about the breakpoints. We can set breakpoints at the parser, at the action, or at the table stage. And a parse breakpoint will be hit when you're parsing that part of a packet. A table breakpoint will be hit when you try to match a table, and an action breakpoint will be hit when you do the action. So we're going to now inject a packet. First we need to SSH to our server. Login as root Netronome. There's an interface here called P4P1, which is our regular NIC, and we're going to use that to inject traffic. So I'm going to send in a UDP packet. And if the program then runs, the breakpoint is hit because that UDP packet is now in the system. We can view, using the View Debug Windows P4 Inspectors menu, we can go and view this packet. For example, view the metadata of the packet. We can also see that the packet headers have been decoded. So these are the headers that actually came from the local memory. So this is a result of parsing that we are seeing here. If we continue running through the program, we keep hitting breakpoints. So now we see Ethernet parsing happening, the table lookup happening, the action happening, and if you go to the inspector for the counters, we are showing traffic came through and flow caches were missed here. And so we're basically seeing the execution of a system reflected in the counters. I think what's happening here is there are more packets than what I sent in, probably because there are some IPv6 probe packets going out on that NIC, etc. So that's what's happening here. But you get the idea. You can debug at the P4 source level, put in breakpoints, look at the packets as they flow through the system, and see the counter values. So now that we are able to drop packets, we're going to change our program to make it a proper NIC. So the first step to make it a wire is to have a forwarding action. And this introduces a new P4 construct called the setting of metadata. So our forwarding action is going to modify the egress spec. And you can modify it by putting in a port number. And this is equivalent of an OpenFlow output action to say, send this packet out on that specific port. So you can see these actions in P4 actually can get parameters and can pass them along to the primitive P4 code that then works with those parameter values. So we also need to go and amend our ingress table to read the ingress port. So now we're turning the table into a table that actually matches something. It matches the ingress port. And the actions, we will also now have the forward action. So if we go and compile this project, we can check whether we did everything correctly. We didn't actually change anything at the control flow level. We just have a more extensive indirect in the in table. Right, so now we need to go to our rules editor and open up our rules and actually create the wire. So here you are behaving as an SDN controller again. And we want to add another rule, and let's call it net-to-host. Where we're going to just make this a bit bigger here. Where we're going to match the port P0. remember P0 is our physical port. And we're going to forward to V0.0, which is our virtual function. So that's the one direction of the wire. Now I'm going to make another direction of the wire. We go host to network, and we match V0.0, and we actually forward it to P0. So we've implemented both directions of the wire. So we can go ahead and build again and debug. So here you can see it's loading the microcode. So it's basically transferring the firmware to the Linux server to load it into the cores. And once again, it remembers we were debugging this specific thread, so this specific thread window is still open. We want to change it to the P4 perspective again. It actually remembered our breakpoints for the ones that still apply. The in table changed. So because of that, that breakpoint was removed because we changed that part of the code. So I'm just going to go and clear out all the breakpoints because we kind of had too many breaks already today. So we're going to go and click on Go to start the execution. And it's running. And let me go and duplicate the PuTTY session to get another window. And look at all the interfaces that are there. So we can see we have the physical NIC, P4P1, just a regular NIC that we're using to inject our test traffic through that loopback wire. And we have the virtual functions. These are the SRIOV NetDevs that we are needing to get the traffic to. So we can do a TCP dump on those. So if I inject a packet, I was actually expecting it to be presented to the virtual function. So let's have an example. Let's have a look at what's happening here. Packet arrived, packet goes to parser start. It passes the Ethernet. It executed our forward action, and we can look at the egress spec. It used to be drop, but if I continue executing and I refresh here, it seems that egress spec is still drop. That's why it's still dropping the packets. What?
Well, it's not for me, for example, because I'm used to programming at a higher level as an operating system where you know, if you can have like a simple Java or Python API where you can write this stuff and say, well, put this stuff in this, just put this big app in, just put this rule in, or even at a higher level where you say, well, actually, route this traffic along this path, and then you can just, get a better, or you can look close in, oh yeah, I'll do this. I guess somewhere between yeah, and then I'm also used to writing software like C, like a software switch in C, which is very simple. It's like whenever, I'm in a select loop, whenever a packet arrives, it's a C script that I can just run in GDB. So yes, this is new to me, so it's very interesting. It's a good learning experience. Things like that. Yeah, it's definitely, it's a more complicated. I mean, admittedly, the known evil versus the unknown evil. But it seems, from a software perspective, it's easier than Verilog, right? But it's not as easy as Java. Something like that. Not as easy as C. But hopefully this is a switch back for you guys, basically make it so you don't have to auto refresh. Like debug twice. Is it the wrong interface or something? That's why it's getting wrong.
I don't really understand quite what's going on here, but this is actually quite good because it illustrates the debugging process. So I made a mistake somewhere. I need to figure out what's going on. There are more packets than we would expect because we're just supposed to do TCP replay. So something else on the system here is generating packets that we didn't expect. This counter is way too high. We didn't send 28 packets.
But all the specs which you see saying it's clock, right? None of them is actually matching the flow entry which you have.
Yes, it's not actually sending to the host. What we would expect is TXNFD would be incrementing if it was sending to the host. So for some reason it's not actually matching here. Okay, so to conclude, what we have seen is the ability to conveniently create a project file, add code to it, add rules to it, debug packets as they flow through the system by using code breakpoints, etc. So hopefully you've had experience on your tables as well from following along here. Or maybe just pause for questions before we hand over to the next lab. Okay.